So as I told you that this is not a very technical one. This is just quantum mechanics along with Bell's theorem. So let us start with some basic. All we know that Bell's theorem has been very important after this, at least it was, but it became more famous after these three people got Nobel Prize because they performed some experiment on Bell's theorem, proving Bell's theorem rather. And their experimental results show that microscopic world, quantum mechanics has contradiction with local realistic theory that is well known, but these their experimental results show that microscopic world behave in a way that is in contradiction with Einstein concept of nature. So let us review very briefly the quantum mechanics. Quantum mechanics, you know that there had been some experimental results which in no way could be explained by classical theories. So at certain point of time, people started to postulate various new kind of things which goes against classical worldview. Max Planck started it, then Einstein joined, and then many people like Bohr, Heisenberg, Schrödinger, they joined. And finally, in 1926, this formalism of quantum mechanics was established, but in a concrete form, it came in the book written by John von Neumann, and title of the book is Mathematical Foundation of Quantum Mechanics. We generally follow the postulates enunciated in this book by von Neumann. So little bit let us describe what is quantum mechanics. So quantum mechanics starts with some principle which tells that every system should be associated with a Hilbert space, and states are given by unit vectors in this Hilbert space.
Hello, sir.
Yes.
You can make your slide full screen.
Full screen, yeah. I forgot. Yeah, now it's okay, no?
No, sir, it is not yet.
Yeah, but I have done it. In my computer, it is showing to be full screen.
Can you please close the slides and start again?
How to close? Escape.
Like close the window and then open the slides and make it full screen again.
Now, I've done it again.
It's still showing not full screen.
Shall I do a stop share and then start?
Yeah, you can try that once.
Now?
Yeah, now it works.
Yeah. That's why it's not moving. Yeah. Okay. And so, as I told you that I am not going to the most general description of quantum mechanics like density operator and all these things. So I keep myself simple. Like states are represented by vectors, which will be sufficient for my discussion, and observables are associated with self-adjoint operators. And you know, every self-adjoint operators will have set of eigenvalues which are real, and correspondingly there will be eigenvectors. And there is a rule. Why yes? And there is a rule which is called Born rule, which tells you how to calculate the probabilities of various results, because quantum state does not tell you definite value of a particular observable. But if observables are given, states are given, then you can tell with which frequency or with which probability you can get a particular result. And there is a rule which takes to calculate, you have to take the scalar product between this initial state and corresponding eigenvectors, and take the scalar product, take the mod and square it, then you get the probability. So this is the rule. And there are some examples like if you consider spin observables, the spin observables are simple because they have only two different results like up spin and down spin. So there are there are spin operators. In particular, spin observable along z direction is represented by these two cross two matrix having these two eigenvalues and having these two eigenvectors. You should remember that eigenvectors are represented for up spin, this up one, down one, but sometimes I give the name it to be QIQT0 and QIQT1. Similarly, there is sigma x, again having eigenvalues +1 and -1, and these eigenstates are plus and minus, which are nothing but equal superposition of 0 and 1. And similarly for sigma y. And if I go to the rule of the quantum mechanics, so if this is my initial state, which is nothing but QIQT0 state, and if someone measures sigma z, I mean the spin measurement along z direction, then the measurement results is definitely 1 because here the probability is 100%. But if instead of making sigma z measurement, if one makes spin measurement along direction x, again results are up or down, I mean +1 or -1. But now the probability, because the initial state is not an eigenstate of sigma x, so probability of up spin and probability of down spin are equal, and both are equal to half. And similarly, if the initial state is eigenstate of sigma x, but you perform measurement of sigma z, again both results are equally probable. Up and down are equally probable. Similarly, so there is a nice uncertainty relation which can be expressed in terms of spin. Like there are some states for which particular observable like sigma z is completely certain because the probability of finding half is 1. But sigma x for that particular state becomes completely uncertain. Similarly, if you take eigenstate of sigma x, then sigma x is completely certain, but sigma z becomes completely uncertain. And you can check that there is no state for which sigma z and sigma x both are certain. You cannot find it. Like position and momentum, there is no state for which both position and both momentum are very precisely defined, which is expressed in terms of uncertainty principle first given by Heisenberg. Now, I don't know whether, yeah. Now Einstein did not accept the interpretation of quantum mechanics because quantum mechanics is telling that if you consider a state, then there are certain observable whose value can be told deterministically, but there are other observables for which there is no particular value. The value will appear when you perform the measurement with certain probability. This interpretation could not be accepted by Einstein, and you know, in various Solvay conferences, Einstein and peoples in board camp, they had bitter fight upon this thing. Now let us see how Einstein used to think. So consider a particle maybe in a big box, then box is divided in two boxes. Now the quantum state, this is a possible quantum state that though the box are far away, this quantum state is a valid quantum state. 1 by root 2 QIQT B1 plus 1 by root 2 QIQT B2. B1 represents the state when the particle is in B1. Similarly, B2 means particle is in B2. But in quantum mechanics, this is also a valid unit vector, so this is also a valid state. Now, so this is a valid state, and you don't know, according to standard interpretation of quantum mechanics, the particle is as if nowhere. When you perform the measurement, I mean, you try to know where the particle is. So you open one of the box, then particle will appear either in this box or that box. Now, Einstein is telling the two box may be far away. Let you open this first one, left box, and you find there is no ball. Then the ball will be, because there is a single ball, so ball must be there in the second box. Now Einstein is telling, so initially according to your state, the ball, you cannot tell that ball was there in the second box, but your observation on one of the box can immediately tell. And if you don't find any ball in this particular box, then you can immediately conclude the particle box is in the right one, which may be very far away. So it is a non-local effect. Ball was not there. My observation creates the ball to be in the second box. So Einstein used to think this is a non-local effect. So in some sense, in quantum mechanics, there is some elements of non-locality he used to believe. But one thing I should tell, though Einstein used to give such examples, Einstein could never show that quantum mechanics has contradiction with relativity. I mean, principle of relativity, something moves faster than light or something moves instantaneously. Einstein could not show this thing, but in some sense, Einstein could used to tell that this is kind of non-local effect. But he could not convince other people because he could not show that it has some contradiction with relativity principle. So Einstein used to tell, like, if the ball is not there in a particular box, then what is meant by position measurement itself? But Pascal Jordan, Niels Bohr, they had some answers. Pascal Jordan used to tell, observation not only disturb what has to be measured, they produce it. That means Pascal Jordan used to tell that observation, there is no particular value for this observable, but observation only created those measurement results, which Einstein could not concept. There is another statement. We compel the electron to take a definite position. We ourselves produce the result of measurement. Like if there is an electron in a box, according to Stern interpretation of quantum mechanics, at least what Pascal Jordan told, I say electron has no position, but when you perform a measurement of position, then you compel the electron to take a definite position. Similarly, Niels Bohr used to tell it is wrong to think that the task of physics is to find how nature is. Physics concerns what we say about nature. So there is no independent reality independent of our consciousness. As if when our consciousness intervenes, some results are created. These are the viewpoints of people belonging to Copenhagen interpretation. But Einstein's response was God does not play dice with the universe. So there had been so many debates. Now, let us be very precise. So there are two principles, though I don't tell sometimes this one as uncertainty principle, but because they can be derived, that's why I sometimes term it to be uncertainty relations, because this can be derived. Now, question is, there are some pairs of observables like position, momentum, and spin along different direction, polarization measurement along different directions. So there are some pairs of observable which satisfy uncertainty relation, implying there is no state for which both the observable will have precise value. So spin observable are nice examples. As I told you, you cannot find any state for which both sigma x and sigma z are precise. Examples of such pair, as I told you, position, momentum, spin into different direction, etc. And this is famous uncertainty relation first discovered by Heisenberg. So this is one. Another one is complementarity, which was propounded by Niels Bohr. There are pair of observables that cannot be simultaneously measured. Again, position momentum pair, the pair of two different spin measurement, and the pair of wave property and particle property in an interferometric setup. These are examples where you can have two observables which cannot be performed, which cannot be measured simultaneously or jointly. Now, question is whether from these two you can come to the conclusion that a particle cannot have definite position or definite momentum or definite spin before measurements are performed. At some point of time, Einstein accepted this thing, this uncertainty principle, after big debates and complementarity or incompatibility of observables. But still, he accepted these two, this uncertainty principle and incompatibility of observable. That means there are certain observable like position, momentum, which nature does not allow you to measure jointly. But still he used to believe that individual particle possesses determinate values to be revealed in measurement. And he was logically correct. The uncertainty principle only prohibits the possibility of preparing an ensemble of system in which all those properties are sharply defined for each particle. This will be cleared after certain slides. So this statement tells that uncertainty principle cannot tell that particle cannot have definite position. I mean, individual particle cannot have definite position, definite momentum, definite spin. This does not follow from uncertainty principle. Similarly, we cannot measure the definite position and velocity or momentum of a particle at one instant of time. That's true. That was accepted by Einstein. But it does not tell us that the particle at any instant of time does not have the definite position or definite momentum. You cannot measure, that does not immediately imply that particle cannot have definite value for all those observable like position, momentum, or spin. This was the standpoint of Einstein. So quantum mechanics is a probabilistic theory, and Einstein used to believe that any fundamental theory of nature that has to satisfy these two. Fundamental, if it has to be a fundamental theory. So according to him, quantum mechanics is a probabilistic theory, it cannot be fundamental theory. Maybe in future there will be some fundamental theory and quantum mechanics will be seen as a statistical theory over those fundamental theory. So Einstein used to believe that any fundamental theory will have these two properties, like it will be realistic. I mean, every observable will have definite value that will be revealed in future measurement, and the theory should be local. That means it should not allow any action at a distance. And obviously, he used to believe that measurement does not create but reveals predetermined values for observable. But in 1935, Einstein, when trying to find that there is some elements of non-locality in quantum mechanics, but he could not, he gave various examples, but he could not establish that, as I told you, that quantum mechanics has some contradiction with relativity. Finally, using this reality and locality criterion, he could show, he claimed to have proved that quantum mechanics is incomplete. So quantum mechanics is not consistent. Quantum mechanics is not wrong, but quantum mechanics is an incomplete theory, according to this. Now consider a spin state like A0 plus B1. Quantum mechanics tells for this state, sigma z has no definite value according to Copenhagen interpretation. But we can give a different picture also. Like we can tell, if you prepare large number of copies of this state psi, then n into mod a square number of them will have sigma z plus 1, and n into mod b square of them, for them, sigma z is equal to minus 1. Similarly, for the same state, if the same state can be expressed in different basis, I mean plus basis and minus basis, it can be written as C plus plus D minus. Then also you can claim that every individual particle has definite values for sigma x also. But if you prepare large number of psi, then n into mod c square number of them will have sigma x is equal to plus 1, and n into mod d square number of them will have sigma x is equal to minus 1. And these will be consistent with observable statistics. So this seems to be consistent with quantum statistics. So why unnecessarily, Einstein used to think, why unnecessarily this Bohr and Heisenberg and all these people is telling that before the measurement, particle cannot have definite speed. But von Neumann rejected this possibility in 1932 in his book, as I mentioned, Mathematical Foundation of Quantum Mechanics, and later actually there had been some mistake by von Neumann, and he claimed that quantum mechanics cannot have a quantum mechanics cannot be replaced by hidden variable theory. But he was wrong in his. Now let us come to the EPR argument. So EPR argument is telling reality they have defined in a very concrete way. If without any way disturbing a system, we can predict with certainty the value of a physical quantity, then there existence elements of reality corresponding to that quantity. And I think it is very profound kind of definition. and it is sufficient condition for reality. Some people describe it to be sufficient condition. And locality is very common sense assumption. If systems are spatially separate, the disturbance on one system does not instantaneously affect the reality that pertains to the other system. And criterion of completeness means every element of physical reality must have a counterpart in the physical theory. I mean, if you can derive some kind of physical reality from the theory itself, then those reality should have a counterpart in this physical theory. If it is not, then you cannot tell that theory is wrong, but you can tell theory is incomplete. And with this thing, Einstein wanted to prove that quantum mechanics is incomplete. For that, actually he considered a state like this, but this was Bohm's version. Einstein actual proof was in terms of position and momentum, but Bohm modifies it. Now consider a state like phi, which is a Bell state, and it can be written as 1 by root 2 0 0 plus 1 1. But the state has a nice property that it can be expressed in the same form, but write in a different basis, which is eigenstate of sigma x. So it is plus 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 minus minus. So properties results are completely correlated if both measure spin in the same direction. So I mean, if both measure sigma z, their results either both are up, both are down. Similarly, if they both measure sigma x, then again both their results are either up or both of their results are down. Now consider a situation when these two particles can be light years away. Now, if you consider a thought experiment like this, if someone performs sigma z measurement on this particle, he can immediately tell what is the sigma z value of this particle too, because results are completely correlated. If he gets up, he knows that sigma z for this second particle is up. If he gets down, he knows that it is down also for the second particle. But measurements on this system should not disturb the reality of this other system. So you can conclude that even if you don't perform any measurements, this second particle has a definite value for sigma z. But the same argument can be made for sigma x also. So you can conclude that sigma x has a definite value for particle 2. So then for a single particle, you can tell that this reality and locality argument, they are telling that sigma z and sigma x both are real. But quantum mechanics can never accept. Quantum mechanics cannot assign values for both and hence incomplete. This was the conclusion of Einstein-Podolsky-Rosen paper. But I must tell you one thing, because there are some wrong conception. So that's why I am telling that why all this EPR argument and this, it has nothing to do, it has no contradiction with relativity. Let me, to establish that, I have considered two boxes. So one box contains large number of particles, maybe 1 lakh particles, and half of them are in 0, half of them in 1. And box 2 again contains maybe 1 lakh particles, but half of them are in plus and half of them are minus. So box 1 is this thing, box 2 is this thing. Now I give you the box, say, without telling which box it is. So so I give you the box, and by measuring and whatever you can do, you have to tell which box you have been given, box 1 or box 2. And I am telling all these students, at least those who are beginners, that you can never tell. Either you have been given box 1 or box 2. Because if you take any self-adjoint operator and calculate the expectation value according to Bond's rule for box 1 and box 2, you will get the same result. So these two ensembles cannot be discriminated. And this has a nice implication. So if you consider a state phi plus, say 1 lakh phi plus between Alice and Bob, who may be light years away, they can, if these two boxes could be discriminated, then actually you can send information instantaneously. How? Because if they share states like phi plus, then they want to transform some information like like there has been a cricket match between India and West Indies, and Alice has to inform Bob that whether India has won or India has not won. India has lost. So this can be done immediately. How? Even if he light years away. How it can be done after the match ends? Alice will perform sigma z measurement on all of them if India wins. And if India lose, then he'll measure sigma x on all these particles. And you can see that if India wins on Bob's side, this ensemble will be created, like box 1, 50% 0, 50% 1. And if India lose, then because of this measurement by Alice on Bob's side, this ensemble will be created. I mean, 50% plus and 50% minus. And if these two can be discriminated, then Bob can know the result of the matches immediately. I mean, even if they are light years away. So quantum mechanics, you see, quantum mechanics does not allow, because these two boxes cannot be discriminated. That's why quantum mechanics does not allow superluminal signaling. So now, and this is not a general proof, but I am telling you in Krauss's book, State Effects and Observables, you can see there is a general proof which tells that whatever general measurement you perform on one of the particle, it does not change the density matrix of the other side. So quantum mechanics does not allow superluminal signaling. Now, Einstein told that quantum mechanics is complete based on two assumptions, reality and locality. But John S. Bell, while disproving von Neumann's proof, asks a different question. He asks this question, that is it true that quantum mechanics is compatible with reality and locality assumptions made by Einstein? First, this has to be checked, because Einstein using reality and locality is trying to tell that quantum mechanics is incomplete, but Bell's question is more fundamental. John S. Bell is telling, let us first check whether quantum mechanics is compatible with the twin concept of reality and locality. And John Bell did a marvelous thing. He considered two systems, which is two systems far away. And on one of the system, he considered two observable, A1, A2. And on another system, you consider another two observable, B1 and B2. And all possible results are always +1 and -1, like this. Now, John Bell in 1964 and Closer, Horne, Simony, Holt, these people derived in 1969 using this assumption of reality and locality, this inequality. I mean, collection of 4 statistics, you combine them in a different way. First 3 are plus, last one is minus. I mean, you perform measurements of A1, A2 randomly, B1, B2 randomly, collect the statistics and calculate this quantity, which is called Bell quantity. And they could show that if reality and locality assumptions are made, then this quantity cannot go beyond 2. Absolute value of this quantity cannot go beyond 2. It should be bounded by -2 and +2. And they could also show that for proper choice of entangled state and quantum measurements, this quantity can be made to be 2√2. Then Bell could immediately conclude that quantum mechanics is in contradiction with the twin concept of local realism, which was propounded by Einstein. This is a very, very profound result. And now we know that experimentally it has been verified. So Bell theorem can be enunciated in a different way. Not only quantum mechanics, but nature is in contradiction with the twin concept of local realism. I am giving this talk. I have worked on some versions of Bell's theorem, like Hardy's theorem and other versions of Bell's theorem. But in some way, after looking this Mermin's proof and some proof by Maccone, I thought that for students, there is a very, very simple proof. And today, as I told you, I am not going to tell any of my work, but I am going to describe the simplest one version of Bell's theorem. And I think even beginners will understand it. So you can look at this paper, Lorenzo Maccone, American Journal of Physics, 81, 2013. So for Bell, you see, this is in some sense simpler because there have been two possible measurements on both sides, A1, B1, A1, A2 on one side, B1, B2 on the other side. But here, there are three settings, three measurements, possible measurement, 1, 2, 3 on both sides. And measurements results are +1 and -1, which sometimes in the measurement setup can be revealed by some glowing of some bulb like red light or green light. Now, there is a source in between these two detectors, and the source is producing these two particles. The particles are going in different directions and going to this detector. And in the detector, there are two people who randomly measure either observable 1 or observable 2 or observable 3. Let this is repeated, say 1 lakh times. Measurement statistics has been calculated. And after looking at these measurement statistics, these experimenters revealed two observations. The statistics generated from these measurements satisfy two properties. First property is when they both measure same observable, like both measure 1 or both measure 2 or both measure 3, for same measurement, the outcome are also same. In those cases, either both get +1 or both get -1. These are the feature of the statistics. First feature. Second feature is the probability of having same outcomes when both sides for different measurements. I mean, when they perform different measurements, like first fellow measure 1, second fellow measure 2, or first fellow measure 1, second fellow measure 3, like this, when they don't measure in the same direction, in those cases, the probability of having same outcome is 1/4. Then it can be shown, which is a different statement of Bell's theorem. We can show that these two properties is in contradiction with local realistic theory. I mean, if you somehow get these statistics, then you can tell that the theory which gives you these statistics has contradiction with local realistic theory. So two properties are when they measure in the same direction, then with 100% probability they get same results. And second is when they measure in the different direction, then sometimes they get same outcome, sometimes they get different outcome. The probability of having same outcome for different measurement is 1/4. We will show that these two are in contradiction with local realistic theory. Let us move. See, if you consider if you consider this first particle, in how many ways you give them values? Because you have to assign values for observable 1, observable 2, observable 3. For a single particle, in how many ways you can assign definite values? I think in eight many ways. All are plus. First two are plus, second one is minus. First one is plus, second one is minus, third one is plus. In this way, in 8 possible ways. Similarly, on both sides, there are 8 possible ways. So in total, in 64 many ways, you can assign definite values to these observables. In 64 ways. But you have to satisfy this first condition. So actually, out of these 64 ways, only these 8 are allowed. So if you consider a pair, a individual pair, then if this for this first particle, if both are all are plus, then for the second place it has to be all are plus. Because if it does not hold, then the second one, a first one will be violated. If let these all are plus and here it is plus plus minus 1, then when they both measure 3, then their measurement result will not be same. So this same for same measurement, the outcome are same. This is very, very powerful observations, and these actually restricts these 64 possible assignments to 8 possible assignments, because they have to satisfy this first condition. And so for an individual pair, for a single individual pair, either this will be assignment, or this will be the assignment, or this will be the assignment. In this way, there will be 8 possibilities, and those 8 possibilities will occur with various probabilities. Like first one will appear with, say, P1 probability, second one P2 probability, third one P3 probability. In this way, we can tell let these 8 possible values as value assignments occur with probability P1, P2 up to P8, and of course the sum of these P's will be equal to 1. And the value assignments are already local, as assigned values for observable on one side is independent of choice of observable on the other side. That means you are already value has been assigned for observable 1, 2, 3. So Bob's side, what will be the value of observable 2 for particle 2 does not depend whether measurements 1 is performed on Alice's side, or 2 is performed on Alice's side, or 3 is performed on Alice's side. So measurement results on Alice's side as well as measurement result on Bob's side does not depend on which particular measurement has been chosen on other side. So this is actually locality. So upon this, so we have taken reality as well as locality. Now we calculate these 3 probabilities. So we want to calculate what is the when Alice measures 1 and Bob measures 2, what is the probability that their results are same? Can you help me? I have written P1, P2, P7, P8. Can you verify it? That am I correct? Remember that Alice is measuring 1, Bob is measuring 2, and we want to find the probability, total probability that their measurement results are same. So we have to see the assignment table and find. See so in this case, this set 1 will have contribution. So P1 will come. So Alice is measuring 1, Bob is measuring 2. So P2 will have contribution, I think. Yeah, P2 will have consideration. Then see P7. Both are same. -1, -1, -1, -1. Again, P7 will come. And P8 obviously will come. So when Alice measures 1, Bob measures 2, the probability that their outcome same is P1 plus P2 plus P7 plus P8. Similarly, if Alice measures 2 and Bob measures 3, then P1 and P8 of course will come, but so Alice measures 2, Bob measures 3. So P4 and P5 will have contribution. P4 is this thing. So 2, 3 and 2, 3 are same. And where the other cases? P7, P5. 1, 2, 3, 4, 5. Yeah, -1, -1, -1, -1. So in this way, you can also calculate when Alice measures 1 and Bob measures 3, what is the probability that their outcome are same? It is given by P1 plus P3, P6 plus P8. These are very simple. So now we calculate sum of these three probabilities. Probability of these same results for setting 1, 2, setting 2, 3, and setting 1, 3. We add these results. And it is P1 plus P2 plus P3 plus P4 plus P5 plus P6. All P's will come, but this P1 will appear thrice and P8 will appear thrice. So this will be the expression. And P1 up to P8 is equal to 1. So it will be 1 plus 2 into P1 plus P8. And whatever choice of for P1, P2, P3, etc. you take, this sum of these three quantities must be greater than or equal to 1. Yes? I'm talking. Yeah, sorry. So sum of these three probabilities must be greater than or equal to 1. Because whatever value of P1, P8 you choose, the value cannot go below 1. But this is violated by the second property, which tells that probability, all these probabilities should be 1/4. So 1/4 plus 1/4 plus 1/4 will be 3/4. And 3/4 is obviously strictly less than equal to 1. So you get this statements to be correct, that if you get these two statistics, then actually they have contradiction with local realistic assumption made by Einstein. Now what you have to show that quantum mechanics indeed can produce these statistics. But there is one more point that I want to make, that in general, to derive Bell's inequality, two assumptions are taken, reality and locality, and where reality is taken to be generally considered as an assumption. But Bell himself started with those reality which can be established by EPR argument. EPR argument, how reality is established, already you have told that reality means if you, without disturbing the system, if you can predict the results with 100% probability, only then you can tell that this is something real. So, but generally, when we derive Bell's inequality, we take reality to be an assumption, generally considered to be an assumption. But this is not in general true, that this assumption is itself EPR reality. Why I am telling? You consider any non-maximally entangled state. Then by EPR criterion, you can tell that sigma z has definite value for both the particle 1 and particle 2. If the state is A00, B11, where AB neither 0 nor equal to 1 by root 2. That means it is not a maximally entangled state. But these non-maximally entangled state also shows violation of Bell's inequality, not by the amount 2 root 2, but by this amount, 2 into root over 1 plus 4 squared b square. But when AB are non-zero, and I have considered them to be real, you can take to be complex number also, then you have to take mod a square, mod b square, but they are certainly greater than 2. So Bell's inequality is violated. But here, you cannot claim that reality is EPR reality, because because to find Bell's violation, you have to consider another observable on both sides. And for those observable, reality cannot be established by EPR criterion, because when you write this state in terms of other bases, it does not take this form. This form is violated. I mean, it is not in this Smith form. So this is a unique Smith form. If you write in plus basis, plus minus basis, then it will have 4 terms, and you cannot argue in the way Einstein, Podolsky, Rosen argued. So here, when you show violation of Bell's inequality for non-maximally entangled state, Here, the reality is an assumption that cannot be claimed to have been derived by the EPR argument. And only maximally entangled states allows to establish EPR reality for more than one observable. But here, we will give an example given by Maccone, where not only it is reality in the EPR sense. That means it can be, the reality can be established by the EPR argument. So now we are coming to the quantum example, phi plus, and phi plus can be written in many bases. We have considered only 3 bases, A0, A0 plus A1, A1, where A0 is a standard 0 and A1 is a standard 1. Similarly, this same phi plus can be written as B0, B0 plus B1, 1, 1, where this B0 is some combination of 0 and 1, this combination. 1 half 0 plus root 3 by 2, 1. And similarly, B1 is orthogonal to B0. And for setting, for phi plus can also be written in C0, C0, C1 of C1, where C0 is again some linear combination of 0 and 1. And C0, C1 again orthogonal. And see, phi plus has same form for all these 3 bases. And our measurement is, first measurement is measurement in the basis A0, A1. That means measurement in the basis 0 and 1. Second measurement basis is B0, B1. And third measurement is measurement basis is C0, C1. Now, already, if both measures in the same direction, so this is measurement setting 1, this is measurement setting 2, this is measurement 3. Now, by just looking at these states, you can see if Alice and Bob measures in the same directions or same basis, their measurements are strictly correlated. Because if both measures in the setting 1, then either both get up or both get down. Similarly, both measures 2, then either both get up or both get down. Similarly, both measures in setting 3, that means in C0, C1 basis, it should be C1. There is a mistake. C0, C1 basis, again, their measurements results are completely correlated. Either both are up, both are down. So first condition is already satisfied by this quantum state. Now come to the second condition. Now Alice is measuring in first basis and Bob is measuring in the second basis. So what we do, we express our state phi plus in terms of this basis A0, A1, B0, B0, B1. A0, A1 for first particle, B0, B1 for the second particle. And the expression is something like this. Now, if Alice measures in A0, A1 basis and Bob measures in B0, B1 basis, say their measurements are same with probability 1/4. Because A0, B0 will appear with probability 1/8 and A1, B1 will also appear with probability 1/8. So 1/8 plus 1/8 will be 1/4. And similarly, you can calculate for the second case also. You will see that probably where Alice is measuring setting 1, Bob is measuring in setting 3. Again, you will see their measurements are correlated with probability 1/4. And similarly, when Alice measures in 2 and Bob measures in 3, again, after some calculation, you will get it will be 1/4. So in total, the sum of this thing is 3/4. Again, compatible with this assumption. The probability of having same outcome on both sides for different measurement is 1/4. So this quantum example satisfy both this condition 1 and condition 2. But already we have seen these two properties has contradiction with local realistic theory. So you can obviously conclude that quantum mechanics is in contradiction with local realistic theory. So I hope that before time I could establish what I wanted to tell. But for students, I have some final words to tell. So you must remember, you will never accept if someone tells that quantum mechanics has some contradiction with relativistic theory, that something in quantum mechanics can move faster than light. If that something is some material or some real information, then you be sure that any information or any material particle cannot move faster than light in vacuum, or it cannot move from one place to another place instantaneously. And quantum mechanics does not tell that it is possible. So quantum mechanics respects relativity principle and hence does not allow superluminal transfer of signal. Now, generally we tell quantum mechanics is non-local. Then are we incorrect? Okay, we are not incorrect. When we tell that quantum mechanics is non-local, we mean that the theory cannot be reproduced by local realistic theory. In this sense, quantum mechanics is non-local, not in the sense that quantum mechanics allows superluminal signals. Quantum mechanics is termed to be non-local only to mean that it cannot be reproduced by local realistic theory, for which we already saw a very simple proof. Now, whether this non-local property of quantum mechanics may have some applications, then I must tell that it has real application. That means using this non-locality, though it does not allow superluminal signaling, using this non-locality, you can perform many tasks that cannot be performed in classical world. That means that cannot be performed in a local realistic world. And classical world is indeed a local realistic world. So non-local property has real practical application. That's why this title of this conference is Quantum Information and Quantum Technology. So not only that, yes. Yeah, are you telling me something?
Oh, that's fine.
Yeah, I am finishing. So this non-local property has real practical implications. In particular, it finds application in quantum cryptography, not only quantum cryptography, it finds application in device-independent quantum key generation of random numbers, and many communication tasks. Yeah, I have no slide telling you thank you, but I thank all of you for your patient hearing.
Yeah, thank you, Professor Guruprasad, for what a wonderful talk. And I'm sure that a lot of students also enjoyed it. So so we have 5 minutes for question and answer session before we start the next round. So questions, anybody wants to ask can raise a hand or just simply ask.
Sir, I have a question.
Yeah.
So my question was, say you assumed determinism and
yeah.
So you assume that all measurements results are either +1 or -1.
Yeah.
But if we drop that assumption and assume that there is some real value that it can take, the probability is some, let's say alpha or something, then can this be proved also in that scenario?
Actually, I told one of my students to do it, that take stochastic hidden variable theory, I mean probabilistic hidden variable theory. But I think after some step, it will come to the conclusion this is the only possibility. I hope.
Oh, so you mean that for any
even
other
if we start with probabilistic hidden variable theory, after to fulfill the condition 1, after some steps, it will come that these value, as I said, each sets will appear with various probability. Only that.
Oh, okay.
But I told my student to do this step. They didn't do it. I will request you to do it yourself.
Okay, sir.
So you start with probabilistic hidden variable theory, but assume the condition 1, this property 1, and after some step, I hope that you will come that these are the only possibilities.
Okay.
That determinism is the only possibilities.
I see. But then condition 2 will change. No.
Condition. I mean, you have to show that not only these two these two features are in contradiction with deterministic hidden variable theory. It is in contradiction with stochastic hidden variable theory.
Okay.
I think you can do it yourself, I think.
Okay, sir, I'll try.
Yeah.
Okay,
Very nice question. I appreciate.
Any other question? Yeah. Soumik, can you allow me to open the video camera also? It's not allowing.
Yeah, Chiranjeev, I have a question.
Yeah, please.
Yeah, Guru,
Yeah.
from measurement perspective, this will involve 3 measurements, isn't it?
Yeah.
Each side. And how, that would also have its own uncertainty and things like that, no?
Yeah. So see. So we have seen Hardy's non-locality, Bell's non-locality, Bell's inequality, all these things. So from the start, I told that I am going to give you a very simple proof, but in some sense, if you look at it from experimental side, then you have to consider 3 measurements on both sides. So it complicates the scene. But I tell it very simple for understanding.
Yeah.
What Bell's tells, but not I am trying to tell that for measurements it will be more viable, because you have to take 3 measurements, and if you increase the number of measurements, there is more more error.
Yeah. Thank you.
Thank you.
Yeah, thank you. So any other questions? We have just 2 minutes for another quick question. Well, if not, let's thank Professor Guruprasad Kaur for a wonderful talk. So thank you, Guruda. So
Thank Chiranjeev.
yeah. Very good.
Yeah. Okay.